Let's start the classification of polymers based on the source of origin. Polymers can be classified according to their origin into naturally occurring polymers, synthetic polymers, or semi-synthetic polymers. First, the naturally occurring polymers. Polymers are not just all around us, but they are even comprised within our bodies. Proteins, nucleic acids, cellulose, and enzymes all are examples of naturally occurring polymers. One of the commonly known natural polymers is polyisoprene, or what is known as rubber. Moving to synthetic polymers, we go beyond natural occurring polymers by synthesizing a large number of polymers. Synthetic polymers are mostly made from organic compounds. There are many synthetic polymers such as nylon, dacron, polyethylene, and polystyrene. Finally, the semi-synthetic polymers, which are made by modifying naturally occurring polymers, such as cellulose acetate, known as rayon, and vulcanized rubber. Now moving to classification of polymers based on their structure and the way monomers are connected together. First, linear polymers are the simplest type of polymers. Linear polymers are composed of one main backbone with no branches. The main chain is a long continuous carbon-carbon bonds linked together in a closed packing. The closed-packed structure of linear polymers causes them to have high melting and boiling points, high densities, and high tensile strengths. Examples of linear polymers is Teflon, which is made from tetrafluoroethylene. High-density polyethylene, nylon, and polyesters are also examples of linear polymers. The second type of polymers based on their structure are the branched polymers. In the branched polymers, branches come off from the primary backbone chain. Still, the branches are from the same repeating units of the main polymer. The reason behind the formation of branches is that the monomers of the branched polymers may contain two or more end-functional groups that cause side chain reactions along the primary backbone. The branches cause the polymers to be less packed compared to the linear polymers and have low boiling points and low melting points, low densities, and low tensile strengths. The branches differ in their length and on how they branch off from the main chain. There are many types of branched polymers that are subclassified according to their architecture. For example, star polymers, where single branch point gives rise to multiple linear arms with the same repeating units coming off a center. The second subclass is the H-shaped polymers. H-shaped polymers have primary single chain crossbars at both ends into Q number of branches. If the Q number is equal to 1, it's a H-shaped polymers, but if Q number is equal to 2, it's a pom-pom branched polymers. Comb-shaped polymers have primary backbone chain with two or more linear grafted branches form along the backbone. Comb-shaped considered to be regular if the arms are identical. For brush polymers, the side chains are unbranched side chains coming from both sides of the primary chain with four-way functionality or larger. Brush polymers are used in surface coating as a result of branches repel each other, stretching away from attachment surface. Dendrimers are a special type of branched polymers where many branches cause molecules to form a webbing when cooled. Dendrimers generally adopt a spherical three-dimensional morphology due to the symmetry of branches around the core. The functional groups on the surface of the spherical shape indicate the physical properties of the dendrimers. Commonly, the spherical shape allows dendrimers to act as a carrier either on their surface or inside their core. For instance, design the dendrimer's inner spherical surface to be hydrophobic and outside surface to be hydrophilic allows the use of dendrimers as a carrier for many hydrophobic drugs. The third classification of polymers, according to their structure, is the cross-linked polymers. Now, The branched or linear chains can be further interconnected at several points through physical interactions or chemical bonds to form single macromolecule with three-dimensional network structure. The cross-linked polymers, such as thermosets or elastomers, behave completely different from their counterparts. Cross-linking reactions are usually promoted by heating or photoirradiation. The cross-linked polymers are insoluble in any solvent, and they have the ability to retain water-forming gels. Polymers with a small number of cross-links have good swelling properties and used as gels, where polymers with large number of cross-links are rigid and hard. The interconnection cross-link points can be obtained by physical interactions, such as hydrogen bond, ionic bond, hydrophobic interactions, or coordination bonds. Physical cross-linked polymers can be reversibly dissociated and recombined under specific stimuli such as heating, cooling, or changing pHs. Chemically cross-linkers are used to cross-link polymeric chains through side chain interactions. The chemical cross-linking of polymers produce strong subtle materials comparing to their counterparts, where the high density of cross-links makes polymers hardly swell in solvents. Such materials have good thermal and mechanical properties and high chemical resistance. One example of chemically cross-linked polymers is a vulcanized natural rubber. The heating of natural rubber in presence of sulfur as a crosslinker, or what we call vulcanization of rubber, produces robust form of rubber that is used in car tires. By that, we came to the end of this lecture. In our next lecture, we will talk about the other classifications of polymers, classification of polymers based on mode of polymerization, and the classification of polymers based on molecular forces.